and expertise of students. Seminars help us to improve our knowledge and get updated to the latest technological developments. In higher education, where every aspect of the study is relevant to the market and industrial standards, workshops and seminars are more than necessary. Nanotechnology provides many benefits in many areas of life. It helps to improve many technological and industrial sectors to a large extent, such as information technology, energy, medicine, national security, environmental science, food safety, and many others. In this context, the Department of Chemistry, Ch.S.D.St.Theresa's College for Women, planned to organize a national seminar on rest to function, molecular tools for the manipulation of size, surface chemistry, and assemblies of metal nanoparticles. Hearty and warm welcome to each and every one of you to the national seminar. Prayer has been the natural response of humans to cope with situations in life. Traditionally, we pray to a higher power of God for things of necessity and want. As we are going to start the national seminar, let us look to God in prayer. I call upon Sister Swapna of 2nd BZC to lead us into prayer.
Let us do our daily prayer. Our Father who art in heaven, hallowed be thy name. Thy kingdom come. Thy will be done on earth as it is in heaven. Give us today our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil. Amen. O most merciful God, grant me, I beseech thee, ardently to desire, prudently to study, rightly to understand, and perfectly to fulfill that which is pleasing to thee, for the praise and glory of thy holy name. Amen.
Thank you, sister, for imploring God's blessings. A welcome goes beyond words, creates a feeling of caring, and gives a sense of pleasure. A sincere welcome reaches out and positively pulls guests into the hospitality environment they have chosen and makes the guests feel like they have made a good choice. Nurturing these relationships is a crucial part of growing a successful event. Now, I take this opportunity to invite Dr. V. Nagalakshmi, Associate Professor in Chemistry, to welcome the gathering. Over to Nagalakshmi, ma'am.
Respected Honorable Principal Dr. Sister Marietta de Mello, First Lady of the College, Correspondent and Superior Dr. Sister Marietta Pudota, Vice Principal and PG Directors Dr. Sister Shaurilu, Controller of Examinations Dr. Sister Sunila Rani, our today's resource person, Director of Center for Nano and Soft Matter Sciences, Bangalore, and also Senior Principal Scientist of Physical Chemistry Division of National Chemical Laboratory, Pune, Sri Dr. BLV Prasad Garu, all the HODs and co-faculty of various departments and colleges, and my dear students, a pleasant morning to each one of you. On this morning, it gives me great pleasure and honor to extend a pleasant welcome to this national seminar. A warm welcome to our beloved, compassionate, prayerful, and cooperative correspondent and superior, Dr. Sister Marietta Pudota, to this interesting seminar. It is pleasure for me to welcome our dear principal, Dr. Sister Marietta Di Mello, who is successfully leading the institute by decentralizing the targets with meticulous planning. Hearty welcome to our motivating Vice Principal and PG Directors, Dr. Sister Shaurilu, who is also an active researcher. It is an honor and privilege for me to extend a genial welcome to our today's resource person, Dr. BLV Prasad Garu, an accomplished scientist with several publications. Cordial welcome, sir. A cheerful welcome to all the heads of the departments, faculty from different departments and different colleges, and my dear young friends. Today we have gathered here to know some interesting areas in nanoscience and nanotechnology. Through this seminar, students will be more aware of nanotechnology, and I ensure that each and everyone will thoroughly enjoy the talk. Thank you. Have a nice and useful day.
Thank you, Miss, for the warm welcome. Today, indeed, we are privileged to have an eminent resource person who is none other than Mr. BLV Prasad Garu in our midst. We are indeed fortunate to have him with us once again to address the advanced research going on in nanotechnology. Before listening to him, I call upon Dr. M. Rama, Associate Professor in Chemistry, to introduce the resource person, Mr. BLV Prasad Garu, to the august gathering.
Good morning to one and all. I deem it my privilege to introduce the eminent scientist, Dr. BLV Prasad Garu. He is performing two positions simultaneously. One is National Chemical Laboratory, Pune, and another one is Director of Center for Nano and Soft Material Sciences, Bangalore. Dr. BLV Prasad Garu had his schooling up to degree education in Vijayawada, that is belongs to Krishna district of Andhra Pradesh. It is very closer to us, around 60 kilometers to West Godavari. Later, he pursued his MSc and PhD degree in chemistry from Central University, Hyderabad, otherwise called University of Hyderabad. After his degree, he joined in National Chemical Laboratory in 2003 and continuing there till now. He has published more than 125 papers in international peer-reviewed journals and has 8 international patents up to his credit. He was invited as a visiting professor by different universities in many countries, including Japan, USA, UK, France, and Germany. His group mainly works in general area of material chemistry, including the most promising area of nanomaterials and soft materials. Their work in the area of synthesis of monodisperse the metal particles and their assemblies, and their efforts in understanding the mechanism of achieving monodispersity in metal nanoparticles is appreciated world over.
Hello?
They were the first group in the world to show
Hello?
the utility of a class multifunctional
ఎక్కడి
biosurfactant
నుంచి
glycolipid boloamphiphilic
వస్తున్నా మిస్
molecules
ఇప్పుడు చూస్తాను
called
మిస్
sophorolipids
ఒకసారి వస్తాను
in the synthesis of nanoparticles. They have then extended these concepts for the synthesis of nanoparticles by continuous flow methods. Their endeavors towards the preparation of polymer nano scaffolds for enhanced cell growth and tissue engineering has generated lot of interest both from academics and industrial communities. So the awards and rewards. So many colorful feathers are there in the hat of Mr. Dr. Prasad Garu. Scientist of the Year, National Chemical Laboratory Research Foundation, January 2009. Material Research Society of India, Medal in 2012, CSIR Raman Fellowship in 2012, Chemical Research Society of India Bronze Medal in 2013, Young Career Award CSD Nano Mission in 2013, elected as a Fellow of the Indian Academy of Sciences Bangalore in 2014, admitted as Fellow of Royal Society of Chemistry FRSC London 2016, elected as Fellow of Andhra Pradesh Academy of Sciences 2017, guest editor Bulletin of Material Science, Icon Facts 2018 special issue, selected for MRSI ICSS Material Science Annual Prize 2020, and selected for CNR Rao National Prize for Chemical Research by CRSI. So these are the different awards and rewards of Dr. Prasad Garu. So we are very fortunate to have such a eminent scientist in our midst today. So dear students, please listen to him and inspired by his area of field of work. Thank you.
Thank you, ma'am, for fulfilling the noble task of introducing our resource person to the gathering. Now it is time to listen to our resource person, Mr. BLV Prasad Garu. Hope to have a successful and meaningful and interactive session. I hand over the session to Mr. BLV Prasad Garu. Sir, welcome you.
Thank you very much. Am I audible?
Yes, sir.
Okay. So good morning, everyone. And this is my second seminar at St. Theresa College. And even the first time when I visited, I was very, very impressed by the enthusiasm shown by both the teachers as well as the students of this, old college in Eluru. And it is now, this is the second time. This is the second time that I'm giving a seminar. Hopefully, once this kind of pandemic gets over, we'll be having more opportunities to visit and then have more easier and then what you say interactive interactions. Unfortunately, online sometimes it's not so easy to have interactive interactions. Nonetheless, I would be happy if you have any questions, please do post in the chat box. I will try to see those chat box questions from time to time and try to answer them to the best of my ability. Once again, thanks to all the organizers of this national seminar, the principal and HOD of the Chemistry Department of St. Theresa College, and also mainly to Dr. Nagalakshmi, who has been always in touch and then keeps on updating me on the progress that has been happening at your college. So let me start my talk, and then as I know, these are mostly bachelor students and probably master students. So I would like to keep it as simple as possible, the talk, and then take you not just the applications of nanomaterials, but mainly what are the fundamental issues that are necessary to be solved if one were to use nanoparticles for a specific application. I will also try to give you an introduction to what is nano, and then why should you or why should we be talking about that particular field of science. Okay, what is so exciting about it, what is so interesting about it, that also I will try to introduce you to you all. So let me start my presentation by sharing my slides. Please let me know whether you are able to see my slides. Are you able to see the slide?
Yes, sir. Yes, sir. We can see.
What is the slide? Okay. It's exciting dragging down You can drive or you can drag a horse to the water, but you cannot make it drink water, right? So that my interest or like my purpose of this talk would be to encourage you to see that this particular field of science is interesting, and therefore it can be of some help, right? That's why if you can see my presentation has been titled little interestingly like dress to function. I'll come back to I will come back to that, like why I titled this talk with the dress to function. Of course, the next, after the colon, whatever is there is basically the technical details of the talk. But if I can impress on you that what is this dress to function, and then how you can understand this particular feature, I think that is more or less solves the purpose. So with that, um, so I would, in my talk, will be using a lot of what are called analogies, and this is basically the Feynman technique. It is what called. I'm sure most of you know who is Richard Feynman. He's a famous physicist and a Nobel laureate, and then was supposed to be very interesting character. So he always used to kind of take small puzzles, solve them, and then through them try to understand the underlying physics concepts. So here, what I would be using mostly, no, I definitely do not claim to be as great as Feynman, but what I would be trying to use is simplify my explanations and create analogies, right? So with this analogy, you should be able to relate to the fundamental concept in science, and therefore probably you will remember it much easier. Okay, so this is what I will try to be doing. Okay, so that's why if you see, instead of putting such a big title like dress surface modification strategies to prepare functional nanoparticles via bottom-up strategies, this entire thing will be simplified to or analyzed to dress to function. This dressing to function is nothing but the dress that we wear, right? And we are all wearing a dress today. And then why are we wearing it? Like, what is the purpose of that dress? And then sometimes we do wear dress depending on the different activities that we do. All those things I will come to that. We also call them for functions. So we will come to that, all those details as we proceed. So, and before that, I also have this duty, because especially Dr. Nagalakshmi told me that the students nowadays are kind of confused, what to do, right? Especially career. We are doing science. Is there good career in front of us? No, we did not do engineering. Is engineering should we have done engineering? So these kinds of lot of confusions are existing in our mind today. And then these confusions are many reasons. For example, like this person on this slide, having friend says, why are you not becoming a doctor? And the teacher says, why are you not becoming a doctor? And then the mother or father says, go for engineering. And some neighbor says, do MBA. And here we are doing science, right? So it's like unfortunately, none of the people surrounding you are telling you to become a scientist or becoming a researcher. Okay, so there is a lot of confusion, especially in young minds, what to do, right? So to me, what to do depends a lot on what I call as C3. That is basically, you need to have clarity, right? Clarity of thought is extremely important, right? And that you need to have. Don't worry about what others say. Be clear in what you want to do. The second thing is to have courage, right? I will come back to that with some few examples. And the third, and I feel most important, and this is very important, especially in the current scenario in Indian context, is curiosity. I think we are somehow lacking this. We are not having sufficient. We are not asking sufficient enough questions. We are not having curiosity. We are accepting whatever it is being said as is. Even if I say something, you should not accept it as is. You need to ask why this is happening. What is this, right? So this curiosity is somehow lacking in the present day generation. Is what my feeling is. Okay, this is my feeling, by the way. So let us go further. Clarity, right? So when it comes to career planning, as I said, what to do, right? Should I become this? Should I become that? Should I become this? First of all, why do you want to choose a career? The reason why we all want to choose a career is to have a good, decent living, right? That means we need to earn money, right? And For earning money, there are many, many different things that you can do, right? So again, be clear. If earning money is what is important to you, and then by no means earning money is, inferior or not a good, thing to say. Many people they want to say, like, especially, with some philosophy, no, 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 earning money is not good, like, we should be this, we should be that. I don't agree to that, right? Earning money, especially, creation of wealth, is extremely, extremely important, right? Absolutely no doubt about it. Okay. And if you want to really earn money, it looks like there are some careers which are really, really good. For example, I can give you hundreds of examples, and I'm sure even in Yelur you can find such examples, where people just do catering and then earn money, right? I'll open up a hotel and earn money. So nothing wrong in that. I don't know why we keep on thinking that no, 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 that is not important, that is not, prestigious or anything. I think, like, no, nothing like that. If you have dignity of labor, go do something that is, like, suits your thing. I'm sure nowadays you can see a lot of these, internationally acclaimed people are called the so-called chefs, right? Chefs, why not? It's not a career, it's a great career option. So go by all means. If that is what it ignites you, or that is what it impresses you, please do that. Okay. So, the another thing that I see is, lot of these rental businesses, so, you do service, right? I took car rentals as an example, but you do service, and then service sector is, picking up like anything, right? So if you want to earn money, do not hesitate to say so, and then start something that makes you rich, right? And here I want to give a small example, because I recently moved to Bangalore and I was very, very kind of surprised. So this is a person called, I don't want to take the names. It is not appropriate for me to take names, but there is a barber who started a car rental company, and apparently he owns 120 luxury cars, including a Rolls Royce, Mercedes, and BMW. What else you need, right? So, be clear, okay, I want to do this, without any hesitation. This is, we want to do this, not to do this. This hesitation is basically what is killing us. Okay. Never ever have that. Okay. The second is to have courage. We all want to, want to be different. You want to be unique. You want to be identified. This is one of the arches that a thing has. In among the 100 people, somebody should be able to tell, oh, Prasad is this, right? So, but we want to be unique and we want to be identified like this person in this image. But what we do is what others are doing, right? If you want to be unique, you cannot do what others are doing and then want to be unique. You cannot do that. If you are doing everything that others are doing, you will be one among them. You will not be unique, right? So if you want to be unique, you need to do something unique. This is another thing that we miss, right? So to have that courage to be unique, right? To hell with whatever this, what other people are saying. If somebody please mute your mic unless you have some issue. If somebody Chittur- Chittumala. Chittumal, can you please mute your mic? Madam, can you please tell Ms. Chittumala to mute her mic, please? Nagalakshmi or the principal.
Sir, pursue చేస్తున్నాం sir. Sorry for the disturbance.
Okay. Yeah. Yeah. Okay. Thank you. Okay. So, this is another thing that you want to be, ensuring that, we need to have that courage to say that, I want to be unique. And here I want to give you examples, right? Again, I don't want to take the names, but, these names will become very clear to you, right? I have given, these days you must have seen in WhatsApp images, etc. Indians are doing very well, fantastic, right? Everywhere. If you look at the CEO of these three big companies, Microsoft, Google, and Twitter, which are the biggest companies of the world today, you know that all the CEOs are Indians, right? So and the education qualifications that they have are mind-boggling. Again, I have again. I'm not trying to say that this is not important or anything. So this is extremely important. Have good education. Go for these kinds of career. Absolutely no doubt about it. But please remember, these three are employers, right? Employees, not employers. They are employees. వాళ్ళు ఒక కంపెనీలో వర్క్ చేస్తున్నారు. They are not the founders of the company, right? So this is the qualification of a person who is working in a company founded by somebody else. Then what should be the qualification of the person that who founded that company? Right? So, if this is the qualification, BE, MS, MBA, almost common everywhere, right? If this is the qualification of a person who is working in a company, what should be the qualification of a person who founded the company, who started the company? This difference, this distinction might be surprising to you. I don't, it's not that you don't know this. We all know this, but somehow we forget to see this. Okay, we want to be these people who are working in a company, but we don't want to be those people who founded the company. Who founded these companies? Again, I don't want to give the names, but what did they do? Microsoft founder, he dropped out of college. He said, I don't want to be doing any education anymore. I have gained enough confidence. I want to start a company, and he started Microsoft company. And today, there is an Indian who is leading that company. But who founded the company? Right? So he doesn't have any qualification like a BE, MS, MBA, nothing. Right? He is a college dropout. Google founders, again, go and find out. This is not, I'm not lying, there is no exaggeration. Right? These are all absolute truths. Okay? Google founders, they started doing PhD, found that no, this is not necessary. I don't want to do any more PhD. They discontinued and then founded the company Google. And obviously today many PhDs are joining that company. Many people with PhD holding, they are joining that company. But the original founders did not have any PhD. Twitter founder, again, he dropped out of the university. In fact, he joined two universities. First joined one university, continued for some time, said, no, this university is not good. Joined another university, again decided, no, this is not giving me the education that I want. Dropped out and then started Twitter. And today, there is a PhD who is leading that company as a CEO. Right? But what I'm trying to say is that you need to have that courage, right? Somehow again, in India, we don't encourage this kind of a thing. In encourage itself, there is courage. Please understand that, right? We need to have that courage, right? That I want to do this. If you passionately do it, and again, one more thing we also don't do is we don't celebrate failures. Let us fail. What is the problem? Let us fail once, twice. You are not a failure until you give up, right? So these are all, I know, you know all these things, but somehow we don't give importance to these things. Okay. With this, I will stop my preaching and then go to the third important point, especially because I hope by the end of this talk, at least few of you want to be a researcher. Okay. And being a researcher is not at all easy, right? But it is a beautiful career, right? It has very interesting opportunities there. And then more importantly, you will be able to say, I discovered something, I found something that is useful to the humankind, right? Again, mind you, all these three companies that have internationally acclaimed and that very, very famous were all founded by a discovery, right? It started with a discovery, for example, for computers, transistors was a discovery. Intel chip was a discovery, right? So, and that chip basically made all the differences, making the computer smaller and smaller, and therefore this Microsoft could survive. Similarly, Google, that search engine was a discovery, and then based on the search engine, that basically made everything different. Twitter, that the ability to post something and then immediately be seen by everyone all over the world is a discovery, and that discovery led to this particular company called Twitter. So research, all these three companies that I am talking about, and many more, are all based on a discovery. And then to discover something, you need to be a researcher, you need to be a scientist. You need not be a chemist, It can be physics, it can be internet, information technology, it can be biology, it can be anything. But you need to be a person with curiosity. You need to find something new, right? That is extremely important, right? So if one were to be curious, now you need to go leave the analogies, go deeper into the subject, right? Here I have talked about surface modification strategies to prepare functional nanoparticles, right? So the first thing that we need to be curious about this particular title is, what are these nanoparticles? Why should we be worrying about it, right? Okay. So, and all of you again know probably by this time what is nano, right? Not in the popular world. Nano means, that doesn't mean a car, or nano doesn't mean anything else, but nano means here a prefix, right? So, and that prefix actually translates to, in scientific term, a number. And what is that number? 10 power minus 9. So nano to us, the scientists or the researchers, means it's a prefix and it refers to a number, and that number is 10 power minus 9. Okay. And as soon as we say that it is a prefix and it refers to a number, the next question, especially all your teachers will ask, is what is coming after nano? What should be coming after nano when we are talking about nanoscience and technology? When you are talking about nanotechnology, what should be coming after nano? Let me be a little more clear here. As I said, nano means 10 power minus 9. Okay. But what should be coming after nano? There are three things. You all know, fundamental units as we call them, right? What are these fundamental units? Is it a nanosecond when you are referring to nanoscience and nanotechnology? Are you referring to a nanosecond? When you are referring to nanoscience and nanotechnology, are you referring to a nanometer as shown here? Or when you are referring to nanoscience and nanotechnology, are you referring to a nanogram? What is that you are referring to, right? And again, the answer is not very, very difficult to predict, guess, and most of you probably know. We all know that when you are referring to nanoscience and nanotechnology, what we are referring to as a nanometer, right? Now the critical question comes. Why? Why should only nanometer be important? Why not a nanosecond important? Why not a nanogram important? Right? So, why? Okay. So again, let me take back. So here, we also mean, or we also understand when we say nano, means something extremely small, right? So extremely small. How much small, right? So this small, big, these are all relative things, right? These are not absolute things, right? These are relative things. So now let us look at the absolute things, not the relative things. Now let us look at nanosecond, right? Nanometer, nanogram, and see whether there is any difference between these three nanos in between them, and then whether that makes nanometer anything different than the other two units like nanosecond and nanogram, right? So let us spend a little more time. So first thing is time scale, that is nanosecond, right? So a nanosecond is obviously 10 power minus 9 seconds. Is it small the way we perceive as nano? As nano means small, right? That is why even the car that was made was named as nano, because that car is the smallest car in the segment, right? It is not a nanometer sized car. It is a bigger car, right? It has several meters length, but it is called nano because it is the smallest car. Similarly, a nanosecond, is it the smallest unit that you can think of, or is the smallest size, time that you can think of, especially in the time scale, right? So all of you are chemistry students, and then you all know that chemistry means, a very simple definition of chemistry means bond making and bond breaking, right? You make a bond, you break a bond. If you know how to do that, you are a very big chemist, absolutely, right? Between different entities, right? But do you know how much time does it takes for a bond to be made, or for a bond to be broken? How much time, right? Let me the first carbon makes 4 bonds. All the rest carbon atoms can make only three bonds each. You can figure out that, and you have to do something. You have to do a small mathematics. So you Don't worry about all this mathematics, etc. But what is important is that the bigness of the number. The number is so huge that such a material, right? And you see, one of the reasons why we must be interested, we are all interested in nano, is because these materials will have interesting properties, right? But when if you make such a molecule with so many number of bonds existing, such a material is not called a nanomaterial. It is called a bulk material, big material, right? And that material will not show any different properties that are otherwise known to you. Make a plastic, you make anything. So this material will behave just like you make a material, like, in normal instances, right? So it doesn't have any new properties. It will not show any new property. So it is not so useful. So what I am trying to convince you is that in the time scale, nano is not small. It is actually very big. So if you let the reaction go for nanosecond, where one reaction takes place or one bond takes formation takes place within 1 femtosecond, then the material form will be so big that it doesn't have any new properties. Okay. Now let us go to the weight scale, right? And here my favorite question to all the students whenever I come is that, take 18 nanoliters of water, 18 nanoliters of water, and then ask them how many molecules of water will be there. And then you know why I'm asking this very specific question of 18 nanoliters, right? Why am I not asking 20, 25, not that. I'm asking 18. What is the reason? The water molecular weight, H2O, is 18. So if you take 18 grams of water, which is 1 mole of water, it will have 6.023 into 10 power 23 Avogadro number of water molecules. Okay. And water density is 1. Therefore, 18 nanoliters means 18 nanograms equivalent, right? 1. So you can easily, 18 grams means 18 cc or 18 ml. So grams per cc, water density is 1 grams per cc. Therefore, you can easily convert this weight into volume, volume into weight, right? So 18 nanograms of water, 18 grams of water is having 6 into 10 power 23. Don't worry about the other numbers. 6 into 10 power 23. And 18 nanograms, you have to simply multiply that 6 into 10 power 23 into 10 power minus 9, right? So if you simply do that, so 1 nanogram of water will have 10 power 14 molecules of water. Again, 10 power 14 is not small at all. It is rather very big, right? And such a water droplet, if you make a water molecule, a water droplet containing 10 power 14 water molecules, such a water droplet will behave like water. It will not behave anything differently. But if, let us say, you want to behave water to behave differently, right? Its dielectric constant should be different. It might, its surface tension should be different, etc., etc. If you want to prepare such a water droplet which is behaving differently than water, you can make it happen. But you know how much of volume that water droplet should be? It should be a zeptoliter. It should be a zeptoliter, right? Such a small droplet. A zeptoliter of water will have 100 water molecules, roughly. Okay. So where is zeptoliter when it comes to nano, compared to nano? 10 power minus 12 10 power, 10 power of magnitude smaller than nano. Another 12 orders of magnitude smaller than a small droplet. So nanogram or nanoliter are not small, they are big, right? So if you want to really measure something and have it unique properties, you need to really measure a zeptoliter or a zeptogram. So again, what I'm trying to say is, in the weight scale, nano doesn't have to be something unique, something different. As we said, we want to be unique. Like nanosecond and nanogram are not unique. They're routine, they're normal. Okay. But when it comes to nanometer, it becomes unique and it becomes different. Right? That is why we are interested in that. Okay. So what is this difference? The difference is, again, go back to our chemistry fundamentals. What is nanometer? 10 power minus 9 meters, right? 10 power minus 9 meters. What is 1 orders of magnitude smaller than nano? That means you have to divide nanometer, 10 power minus 9 meter, by 10. That is 10 power minus 10 meters. What is 10 power minus 10 meters? Do you know what is popularly we refer to it as? It is an angstrom, right? So our atoms, our ions, our whatever, radii, diameter that you think of all the periodic table, you take any element, take an atom or make an ion out of it, especially all the metals, any of those things, the size of that will be an angstrom, roughly an angstrom, right? Like, see, this, we are talking about orders of magnitude. It will not be 10 angstroms. It will be 1 angstrom, 1.2 angstroms, maybe 2 angstroms, something like that. All of them, all the elements on in the periodic table, their sizes, one atom or one ion, even if you take few electrons. So one ion will be roughly in the range of an angstrom. Okay, so an angstrom is one orders of magnitude smaller than nano. Now, if you bring 10 atoms or maybe 50 atoms together, right, or 50 ions together, that size will be 1 nanometer. So what are you doing? You almost reach the limit. You can go to the angstrom level. What you will be dealing with is salt, salts, etc. Again, like right? And if you take sodium chloride or glucose, right, it will dissolve. Will you able to see a molecule? But you can't see that. But still, you will be able to. There are molecules dissolved in that water, right? But if you drink the water, that will be different. Glucose dissolved water and salt dissolved water, they are different because in one there is sodium chloride ions which are dissociated already. In another, glucose molecules are present, right? Each individual molecule is separate. They are all hydrated and solvated, right? In the solvent pool, they are present. So you are able to make an angstrom level entity by using materials that you can handle every day, like salts and then other molecules, right? Now you assemble them. This is one crucial thing that is the most difficult thing, if at all, if you want to think like that. If you assemble few of them and then make a particle out of it, right? If you assemble few of these molecules, few of these atoms, few of these ions, and make a particle out of it, that size will be a nanometer. So when you are dealing with a nanometer sized particle, you are roughly dealing with 100 atoms, 100 ions, and 100 molecules, right? So this material, because they are having so few atoms, and I will explain to you why they are having so few atoms or few molecules, they behave completely differently from bulk material, right? If you make a very small sodium chloride crystal of a nanometer, it will behave differently than a bulk sodium chloride crystal. If you make a glucose nanoparticle, it will behave much differently. But these are very difficult to make, and then very difficult to look at the properties. The kind of properties they display differently are like not so easy. Whereas when you make metal nanoparticles, right? When you make metal nanoparticles of this size, like 1 nanometer, 2 nanometer, or roughly even up to 100 nanometers, right? So they display completely different properties than otherwise expected from bulk metals, and I will be showing some examples. So this is the important thing. A nanometer is unique, special, because you are almost reaching the limit of what you can handle in the laboratory, right? What you can handle in the laboratory, one molecule you can handle in the laboratory using a solvent, good solvent. You can dissolve it and then isolate one molecule or one atom. And if you assemble some of them, they will become a nanoparticle, right? So the entire the chemistry that we do to make nanoparticles is to just do this. Take a precursor, assemble some of them, make a nanoparticle, and then study their properties, right? So if you know how to do this, you are a great a chemist in the nano field, right? And nanoscience field. Okay, so please understand that. Okay, so one order of magnitude smaller than angstrom. Somebody, a clever person in the audience might question, you can also go lower than nano in the length scale, right? You can go to picometers at least. Okay, so
Sir, excuse me, sir.
yeah,
Sir, presentation share screen చేశారా సార్?
చేశానండి.
ఇప్పుడు కనబట్టలేదు సార్.
ఓకే, ఇందాక కనపడిందా పోనీ?
అంటే బిగినింగ్ లోనే, తర్వాత లేదండి. నేను ఇంకా మీరు ఓరల్ గా చెప్తున్నారే.
Let me do that again. I'm sorry, I did not notice it. Now,
సార్ షేర్ స్క్రీన్ వచ్చింది కానీ నా ఇమేజెస్ ఏం లేవు సార్, మీ ఫోటో వచ్చింది అక్కడ. పీపీటీ రాలేదండి.
okay. Let me sharing again. Now tell me that you are able to.
ఓకే సార్.
No, it is not allowing me to share. I'll join again. Just give me 1 minute. Yes. Is it visible now?
No, sir.
No, sir.
Okay. Is my screen now visible?
No, sir, no.
No, wait now. Are these slides now visible or still not visible?
Not visible, sir.
1 minute.
నాకు మెయిల్ పెడతారండి లేకపోతే?
చేస్తాను. ఓకే 1 minute. నేను ఒకసారి ఇప్పుడు Can somebody now?
Yes, sir. Yes, sir.
Okay,
Thank
yeah.
you. Yes, sir.
Okay. I was all showing this, just remember my talk and then go through these slides. So I was talking about Feynman technique. I was talking about career planning. Then I was saying you need to have clarity, courage, and curiosity. Then I said about different opportunities that exist, including the service sector. And I also introduced you to this person who is having a lot of money, though he is simply a barber. And then I said, you need to have the courage to be unique, to be different. But yet we want to be all this, but yet we try to be doing things whenever we want to choose a career or we want to study something, we'll immediately go what others are doing and then try to do the same thing, but we want to be unique. So this is not possible. That's what I was trying to say. And then I gave these examples of Microsoft CEO, Google CEO, Twitter CEO, and then I also told you about Microsoft founder, Google founder, Twitter founder, right? Who are basically college dropouts or discontinued their education and then pursued their goals or with courage, right? They did not worry about, oh, I don't have a qualification, will I get a job or not? Okay, and they are now giving jobs to many people all over the world, right? So that's what we need to understand. Okay, and then I said you need to have the curiosity, and then started telling about what nano we should be worry about, right? I said nano is 10 power minus 9. I said nanometer is the most important thing. And then I said why should it be important, and I showed you these examples that in time scale the femtosecond is the smallest as of now, but it can even go to lower and lower because there is no limit in the time scale. Similarly, in the weight scale there is absolutely no limit, and if you want to really have a material with new properties, you need to really go to jepto liters or jeptograms. But I also told you that in the length scale, right? It is, uh, you know, uh, it is important that you need to have in the length scale nano becomes very important, and therefore it shows very unique properties, and that's what I said. So, and here it is, you can see that there's a very interesting statement. Nano is a magical point on the length scale, is what one famous scientist Eugene Wang said in 1999. It is not really a magical point on the weight scale, or it is not a magical point on the time scale, but it is a magical point on the length scale. Okay, so why are they having so many important properties? One of the main reasons that these nanoparticles have so interesting properties is that Dr. Nagalakshmi, now I have moved to a slightly different mode. So if you are not audible or my slides are not coming, you have to call me on my phone and then try to tell me. Okay.
Okay, sir. Okay, sir.
Yeah. Otherwise, let me just give me one moment. I will do one more thing. I will ask one of my student to join from here so that they can immediately tell me if it is not coming. Okay, just give me. That probably is a better thing because this network is behaving very erratic now for whatever reason. Okay, yeah. I'll be sending you one link. Okay. Please join that meeting and then in case you are not able to listen to me or let me, so you just immediately call me on this number. Hmm? 058. Okay. So please join that meeting. Hmm? Okay. Okay, so why these nanoparticles so important, are interesting properties, So just let me once check with Pooja whether she has. If there is a student, Pooja Deshpande, if she joins, please admit her. You got the
Okay,
link?
sir. Hmm.
Yeah, yeah. Otherwise, I will give you the link. Okay. They will admit you. It's basically AGH, Google Meet, huh? AGH, URFR, URFR, huh? VEG, VEG, V for vehicle. Huh? Yeah. So why are these nanomaterials, why do have they have interesting and important properties? Okay. The reason is that when it comes to nanoscale objects, nanometer scale objects, the number of atoms present on the surface becomes huge as compared to those that are present in the bulk of the material or the core of the material, right? So any surface atom behaves differently because it is under coordinated. The number of bonds that it has is lower than what it wants to have, right? So this leads to a very interesting, changes in their properties. So one of the first thing is to know that it has a better, higher surface to volume ratio, means number of atoms on the surfaces are larger than the number of atoms on the core. Basically, you can see in many cases, especially when you calculate what is the number of atoms on the surface. For example, here number of atoms on the surface are 1, total atoms are 1, right? So 12 on the surface, 13 total atoms, 42 on the surface, 55 total atoms. So you can see that, so the number of atoms inside are less than those that are present on the surface. So, and these atoms are reactive because they are not bonded. The number of bonds that they are supposed to have, they are not having, and therefore they behave differently. Other things also happen. The nanomaterials are in between the gaseous state and then the solid state, right? Therefore, their energy levels are also different, right? So that also brings very interesting properties, or imparts or bestows interesting properties to the nanomaterials. Again, you can see on this slide, these are the gaseous atoms moving freely. These are the solid in a lattice. They are able to only move little bit, whereas nanomaterials are in between. They cannot escape completely. See here, no, in a confined thing, gases also cannot escape. Similarly, nanomaterials also cannot escape, but they are free to move. They undergo Brownian motion like gaseous atoms. So they're kind of in between the solid state and the gaseous state, and that again brings about lot of interesting properties, or bestows interesting properties to the nanomaterials. What are these interesting properties? The melting points, as we know, melting points, we take it as a standard, right? So for a given material, melting point is, this one, that's it. A teacher asks, tell me the melting point of gold, tell me the melting point of iron. So you just tell the number. But now it becomes interesting to know that the melting point of a material depends on the size of the material. So if you make a nanoparticle, it may not show the melting point as it was supposed to show in the bulk material, right? Being shown here is the example of gold. You can see that, this is a bulk material melting point by the nanomaterials melting point. Melting point of the bulk by the nanomaterials melting point divided by the melting point of the bulk. So here it is almost 1, right? When the particle diameter, and then sodium chloride has sodium ions. And what oxidation state does the sodium ions exist? they are in a cationic form, means they are oxidized, right? Like they have a plus oxidation state, plus one oxidation state, means they have one electron less than their metallic counterparts. A metallic sodium atom has certain number of electrons, and then sodium ion has one electron less than that, right? So now if you supply that one electron, a sodium ion will become a sodium atom. But like, don't use sodium as an example, or don't try to make sodium nanoparticles, because sodium itself is very reactive, and if you put it in water, it will catch fire. So a better example could be silver nanoparticles, let us say, right? The starting point for a silver nanoparticle could be silver salt. What is a very easily available silver salt? Silver nitrate. You take silver nitrate in water, put it in water, take silver nitrate salt, put it in water, it will become silver ions, silver plus ions, and a nitrate ions. So if you add now a reducing agent, right? This reducing agent will add electrons to the silver ions. So the silver ions will become silver atoms. There is a huge difference between a silver ion and silver atom with respect to their solubility. A silver ion is highly soluble. A silver atom is not so soluble in water. So what this silver atom will do are so many silver. You are not making one atom. You will make so many atoms, right? Because you will take a silver salt of certain concentration. Generally, we take a millimolar concentration. So when you take a millimolar concentration of silver, it will have so many ions of silver, and when you reduce them, so many atoms of silver get formed. And these silver atoms, as I said, are not so soluble in water. So what will they do? They will call their friends, the other silver atoms that have been formed. They all come together, make a cluster, and then try to precipitate out of the solvent, right? So this is as simple as that, right? If you know how to convert a more soluble product into a less soluble product, more or less you know how to make nanomaterials or nanoparticles. And exactly this is what we do. We don't do much difference. We know those reactions. What will make a more soluble material into a less soluble material. And then like make, and also don't allow the reaction to continue forever. You need to stop the reaction at a certain point of time. So if you know the time when to stop, so that all the material gets converted to a nanomaterial object, your job is done, right? You will make a nanoparticle. So I will show you one small example, like a video, right? I hope this video is visible to you all. Here my students are trying to make gold nanoparticles, right? Because again, it is very easy to show you because of the color change. That is why I am using gold, right? So you take gold salt, which is what is called fluoroauric acid, and then add water to it, okay, to dilute it. As I said, millimolar concentration which you have to take. So you make gold salt of millimolar concentration. And then add a reducing agent, right? Here they are adding a reducing agent called sodium borohydride. Don't worry about it, there are several other reducing agents you can add, and see what happens immediately. You see there is a color change, and that color change is an indication that gold nanoparticles have formed. As simple as that, right? So the entire process, what did you do? You took gold salt, means gold ions. Gold ions are Au3+. Gold is stable as 3+ oxidation state. You added a reducing agent. This reducing agent added electrons to those gold ions, made gold atoms. Those gold atoms came together, made a gold nanoparticle. But by the time gold nanoparticles got formed, no more gold ions or gold atoms were available. So gold nanoparticles got formed, and the reaction stopped. Right? That's it. Right? So you made gold nanoparticles very easily in the lab. If it is so easy, and in fact, these were made not just in I am showing one citation or one reference. So these were first made in 1951 by using a molecule called disodium citrate, which is even more readily available than the example I shown, that is sodium borohydride. But for disodium citrate, you need to heat the solution. So we don't want to do it. That's why we shown the example of sodium borohydride. So if it is so simple to make gold nanoparticles or any other metal nanoparticles for that matter, why is that we are only talking about them now? Why is that they are not already an obsolete science? Why is that still a very relevant science? Why is it so important to talk about them today? There is a simple reason. These nanoparticles are like, so now I will show you what is called a TEM image. It is a transcription electron microscope image. If you take one droplet of this particular solution that we made just now, let me run the video once again. So you take one droplet of the solution, put it on what is called a TEM grid, and then look it under an electron microscope. What you will see is images like this, right? These are basically spherical nanoparticles. Imagine oranges or apples thrown on a, or marbles thrown on a floor, and then you see a photograph, right? What you will see, you might think they are spherical particles, but they actually what you will see is circular discs, because you are basically looking at a two-dimensional projection of a three-dimensional object, right, when you take a photograph. Similarly here, you are putting these gold nanoparticles on a surface, like a carbon surface, and then you are imaging them using a photograph, right? When you image them, you basically see them like a circular disc, right? So if you notice, one more thing is important thing to notice is that each disc is separated from each other, right? Well separated from one another. These discs are well separated from one another. That means that they are not able to come and contact each other. What is preventing that? The thing that is preventing that is basically a layer of charges present on the surface. What are these charges? Here I am showing the example of this other molecule I told you, trisodium citrate. This could be the trisodium citrate present on the surface. That this could be the chloroaurate, unreduced chloroaurate ions present on the surface. So there is a layer of charge present on the surface, and therefore these nanoparticles are also called colloidal dispersions. I am sure you also heard about these terms called colloids and colloidal dispersions. What are the famous colloidal dispersions that you know in the daily life? Milk is a colloidal dispersion. Blood is a colloidal dispersion, right? So milk is a collection of protein molecules which are stabilized by the charges. But if you try to do anything to the milk, you can boil the milk, is okay. But if you try to add anything except sugar, if you try to add anything else, like if you want to add salt, if you want to add some citric acid, lemon juice, whatever it is, what will happen to the milk? Milk will curdle, right? It will basically precipitates out at the surface, and that is how you make what is called cheese or paneer or whatever you want to call that, right? So, and my question to you is, will you be able to make milk back from a cheese or paneer? It is almost impossible, right? So what you did is basically you have broken the charges present on the surface, and these protein molecules have come together and separated the milk from the water, right? So basically this protein all has settled down at the bottom of your vessel. Similarly, whatever you try to do this to these colloidal dispersions of nanoparticles, they irreversibly aggregate and settle down at the bottom of your vessel or a sample soil. And it is impossible to bring them back to dispersed state. This is the dispersed state, as we have seen in the previous slide. There is a nanoparticle dispersion in a solvent. But you try to do anything, they aggregate, and this aggregation is irreversible process, right? So it is of no use, right? Therefore, what I actually give in my talk, I compare again like an analogy. I told you, right? Professor Ferman's example. I will take an analogy. These nanoparticles are just like newborn babies, right? Just newborn babies. Okay, they don't have any protection whatsoever. Okay, they just come out of a mother's womb. All of us were like this. I don't think we wore any dress. We were not karna or anything, right? We did not wear any dress. We just came out naked from our mother's womb. And what will a mother or a nurse who is our caretaker will do once a newborn baby has just come out of the mother's womb? What will they do? Will they go out and then display that baby to all the public saying that Bahubali aaya hai? I don't think. Bahubali Bukadu, we don't say that. What we do, we immediately protect the baby. Right? Protect the baby in a nice, cozy environment, so that the baby is protected from the environment or other bacterial infections or like whatever, cold, sun, whatever it is. We want to protect the baby from that, right? Similarly, now we made these nanoparticles. right? And then like of course later on I will go to know what is this different process, etc. Let me skip this, right? Like, so I'll go straight. Like, so basically what we did is we made these nanoparticles which are almost like newborn babies, and then immediately we wanted to protect the baby with a dress, right? So here also what people thought is, can we protect the nanoparticles, these charged nanoparticles, with a dress or with a coat, right? And what did they think of when they wanted to put a coat on the surface of the nanoparticle? They thought of organic molecules. You made an inorganic nanoparticle of a metal, but you are now coating them with an organic molecule. I will tell you what are these molecules, what is the examples of these molecules. But there are some interesting features that this organic molecule should have. One of the fundamental and most important features that this this organic molecule should have is this particular thing, a capping moiety. It should be able to make a bond. It should be able to make a chemical bond with the nanoparticle surface, right? Therefore, you cannot use an inert alkane molecule. You need to use a functional molecule, a molecule having a functional group, right? So, if you make such a molecule, then you will be able to protect the nanoparticle like this, right? So, you are protecting the nanoparticle using like this. Now, two nanoparticles cannot come together because these springy-like molecules or the string-like molecules will not allow two nanoparticles to come together and then aggregate like I have shown in the previous images, right? So here I have shown how they aggregate, right? Because so they aggregated, they are touching with each other. But once you have these string-like organic molecules, they will not allow you to have two nanoparticles to come together and then aggregate, right? This prevents that aggregation. One more thing I need to, and for that, what you need to have is the molecule should have one capping moiety so that this molecule is firmly anchored to the nanoparticle surface. One bonding should happen, right? So one more thing that this organic molecule should also have is a slightly longer chain length, right? So SCH2, CH2, CH2. I will come back to that in a little while. But please note that in the cartoon that I have shown here, I have put the molecule almost as equal as the nanoparticle size or even bigger than that. But in the true picture, they are not like that. This length will be somewhere around 1 nanometer and this diameter will be somewhere around 10 nanometers. 10 nanometers to 1 nanometer. But just to exemplify or explain you in a more easy manner, I have drawn it like that. This molecule is drawn bigger and the nanoparticle is drawn smaller, but in the actual scenario, the situation is completely opposite. Right? Please note that. Okay. And the first method, or like the first time such nanoparticles were synthesized was in 1994. Okay. Imagine 1857, Michael Faraday made the nanoparticles in the lab first time. Then 1951, Tarkevich used sodium citrate and made the nanoparticles. But it is in 1994 that people could make nanoparticles which are protected by a layer of organic molecules. And therefore these nanoparticles are called monolayer protected nanoparticles. There is one layer of organic molecule that is protecting them, right? What is the advantage of this procedure? The advantage of this procedure is these nanoparticles can now be precipitated, not aggregated. They can be precipitated and redispersed, right? It is like you are I'm sure you must have seen antibiotics these days. They are given like a powder. You add water, they become a dispersion, right? And then you drink the antibiotic. Like that, you can make a powder of these nanoparticles, add a solvent, and they become dispersible again, giving you a very clear solution, right? So as if it is a clear solution, but actually it is a dispersion. There are nanoparticles present. So this particular thing, this precipitation and redispersion, this ability to precipitate and redisperse is one of the greatest advantages that we have today, right? Therefore, we are able to deal with these nanoparticles in a very easy manner, right? And we are also able to do a lot of many other things, as I will explain to you little while later. Okay, so and from here onwards, what we are not now talking about is not really the nanoparticles, but the organic molecule. And what are the functional groups? I told you, right? These functional groups are extremely important that can make a bond with the nanoparticle surface. What are the famous functional groups? It can be an amine, it can be a thiol, or it can be a carboxylic acid. Any of these three functional groups are generally preferred to make functional or monolayer protected nanoparticles. And in the actual scenario, they look like this. A nanoparticle, again, this particular ligand is, or the length of the organic molecule is much longer, it is drawn much longer, but it is not like that. But this particular X group is basically this thing, NH2, SH, COOH, and then you have CH2, 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 CH2 with a CH2, CH3. CH2, CH3 is a hydrophobic moiety. This entire thing is a hydrophobic moiety. Means it doesn't like water, it is like oil. Therefore, these nanoparticles are easily dispersed in nonpolar organic solvents like toluene, benzene, hexane, etc. So now you have a method of making nanoparticles, but making also disperse them in nonpolar organic solvents. These nanoparticles, I call them as dressed nanoparticles. Right? So now you have put one dress on the surface of the nanoparticle. And what are these dresses? Let me now take you to the previous slides that I skipped. Right? You can dress these nanoparticles depending on the season. Right? How do you dress? Basically, you dress depending on the season. If it is summer, you will wear one type of dress. If it is rainy, you will wear another dress. If it is winter, you will wear another dress. Right? Depending on the season. Here, you need to dress your nanoparticles depending on the application that they must be used for, right? Depending on the application. So let me give you another example. So these three, right? So we also dress depending on the occasion or the function, right? So here the function means a particular event that you are attending. Here in the nanoparticle case, the function means the application, what they are being used for, right? So here you know that this particular person is a bridegroom, this particular person is going for a war, this particular person is a mountaineer, just based on their dresses. But here you need to make the nanoparticles dress appropriately so that they can be used for a particular function. Okay. So again, here you will immediately know that obviously this fellow cannot go and then stand in the stadium with this particular dress, right? So people will not probably even allow him to come in there, right? Also, he might be able to do some certain activities in the ground based on this type of a dress. But if he is batting, he need to have additional gadgets. He might have to have pads, elbow guards, gloves, helmet, etc. So we need to also prepare our nanoparticles for certain functions. If our nanoparticles have to do batting, you need to make the nanoparticles suitable for batting, right? So that's what it is, right? Again, this analogy that I told you earlier. Okay. So let us proceed further, right? So again, I want to skip this particular thing, which is more like about our work. So I don't want to spend more time on that. How do you make nanoparticles suitable for different applications is what I want to spend the rest of time that I have. Right? So far I told you about nanoparticles that can be dispersed in non-polar organic solvents, oils, right? And these are probably good for applications like printed electronics. But one of the things that the nanoparticles are highly suitable for applications are drug delivery applications, right? But for a drug delivery type of application, your nanoparticles should be dispersed in water, not in oil. Right? You cannot drink oil, right? So if you want to think nanoparticles as a tonic having the drug, so you need to have these nanoparticles in water. We started with water dispersions of nanoparticles, if you remember correctly, which were the charged stabilized colloids. But we said no, these are not good because they are aggregating, right? Especially if you imagine a charged stabilized nanoparticle and if you put it into your mouth, what will happen is nothing may happen in your mouth or in the esophagus, but once it reaches your gut or stomach, the stomach has high acidic condition. So your nanoparticles will aggregate. So they will not be absorbed by the blood. They will just be excreted out, right? Because they have become bulk materials or bigger particles. They are no longer in the nano size. So charged particles are not good for drug delivery applications. Whereas you have been able to make monolayer protected nanoparticles, but they are not dispersible in water. So to solve one problem, but created another problem, right? How do we again solve this issue? right? So that's what, right? As I said, this so far whatever you prepared, the nanoparticles are good for printed electronics, but they are not good for drug delivery applications, right? So how do you solve this problem? As I said, you have protected the nanoparticle with an organic molecule, but this end group is a hydrophobic group, right? It is not liking water, it is hating water. If you can somehow modify that substrate, right, or modify that end and make it water loving, or in other words hydrophilic, if you can do that, then your entire nanoparticles can again be easily dispersed in water. But instead of charge stabilization, you are now protecting the nanoparticles with one layer of organic molecule, but the other end of the organic molecule is water loving. Therefore, the entire nanoparticles is water loving. It becomes water loving. So you can make monolayer protected nanoparticles, but water loving nanoparticles, right? In the previous instance, you made monolayer protected nanoparticles, but these are water hating nanoparticles, and therefore they are not good for drug delivery applications, but they are good for applications like electronics, energy, etc. Whereas now you modified just the end group of this organic molecule, made again monolayer protected nanoparticles, which are water loving nanoparticles, and therefore these can be used for applications like drug delivery, etc. Right? Here, I will just show you few examples, that have been done in the literature as well as our own group. So here, the first examples to make, water loving nanoparticles or nanoparticles that can be dispersed in water came out by modifying the end group, right? And as I said, this end group, the exposed functional group. This is the bound functional group. This is the head functional group that is bound to the nanoparticle surface, like thiol, amine, carboxylic acid I told you. And this is the exposed functional group. Here you can use sulfonate group, ammonium group, or carboxylic acid group, better carboxylate group. I'll come to those examples. Right? So with such groups, you can make nanoparticles dispersible in water. Right? So here you can see nanoparticles capped by a molecule called PEG thiol. Don't worry about all those details, but there is a thiol molecule and a PEG, polyethylene glycol molecule, which is having an exposed OH group. Right? And OH group, we all know, alcohols are soluble in water. Right? So therefore, are miscible with water. So it is almost like an alcohol present here. Right? So therefore, these nanoparticles are dispersed in water. You can put lot of peptide molecules on the surface of nanoparticles. Again, using an anchoring group, like anchoring amino acid called cysteine. Cysteine has a thiol group. So this thiol group can anchor to the nanoparticle surface, and you can make peptides. And this again makes nanoparticles stable or dispersible in water. Right? You can also use very fancy molecule called deuterions, right, which have both charges, positive and negative charges. The same molecule. It's not a salt. This is deuterion. Right? So deuterion capped nanoparticles are also stable in water. So you cannot do all this. Right? So in our group, we also wanted to make water dispersions of nanoparticles, and then we used, and in the when I was introduced, my introduction was going on, madam told about a particular class of molecule called sophorolipids. Right? So what are these sophorolipids? These are basically derived from carboxylic acid. A particular example is uric acid. But we do very interesting simple chemistry of that. Right? What we do is we take oleic acid, add some glucose and yeast, nothing else. We just add some glucose and yeast, and then it gives these sophorolipids. Doesn't give pure molecule, it gives a mixture, but we know how to convert this mixture into a pure sophorolipid. Right? So if you see this sophorolipid, the oleic acid backbone is almost intact, nothing changed, except that a dimeric glucose is attached to the penultimate carbon through a glycosidic bond. Right? So oleic acid backbone, a glycosidic bond, and through an oxygen, two dimeric glucose. This dimeric glucose is called sophorose. Like sugars are called glucose, maltose, fructose, galactose, all those O's, right? So similarly, this is a sophorose. Because a sophorose is attached to a lipid molecule, these molecules are called sophorolipids. What is the greatness, or what is so interesting about this particular sophorolipid molecule? The interesting thing about the sophorolipid molecule is, as I told you, this carboxylic acid moiety can go and sit on the nanoparticle surface. So it can become an anchoring moiety or a bond-making moiety, right? Whereas the sugar makes this dimeric sugar makes this entire molecule soluble in water. Oleic acid is not soluble in water, whereas the sophrolipid is soluble in water. So now you put a molecule that is soluble in water on the nanoparticle surface, right? And in fact, one more advantage of having sophrolipid is that this is a reducing sugar, right? So it is a reducing moiety as well as a catching moiety. Both of them are existing. This is the reducing moiety, this is the catching moiety. Both of them are existing in one molecule. Therefore, when you make silver nanoparticles, you can beautifully make silver nanoparticles out of using sophrolipids as reducing agents as well as catching agents. Again, don't worry about all those details, but most important thing is these two vials. This one vial is what is called as prepared particles, right? We just add sophrolipids, some silver nitrate, add some base and heat them, and then you will get silver nanoparticles. And this color formation again is an indication that silver nanoparticles are formed. But what is most important is sample vial 2. What is this? You precipitate these nanoparticles. You get them as a powder, but add water. Again, they become dispersible, and they don't lose their properties at all. All the properties are retained. No irreversible aggregation as we have seen in the previous case. So this is a very easy method of making water dispersions of nanoparticles using this sophrolipid molecules. And making sophrolipids is not at all difficult. You just have to take oleic acid, which comes from your coconut oil. Coconut oil has oleic acid, linoleic acid, linolenic acid, etc., etc. So you take oleic acid out of that. All this, these are called MUFAS, mono-unsaturated fatty acids, or PUFAS, polyunsaturated fatty acids. These are present in your good oils, right? Like sunflower oil, palm oil, coconut oil. So these are all present. So you take oleic acid out of them, and then you add some yeast and glucose. And in our group, the students say that yeast does the rest. I don't have to do anything because it makes the sophrolipid. Then you have to do small purification step to get oleic acid sophrolipid molecules or acidic form of sophrolipids. So once you make these sophrolipids, you simply take the sophrolipids, add some metal salt like silver nitrate, add some base, and then heat them. You can also make gold nanoparticles. So that's it. You will have nanoparticles, and then you can precipitate them and redisperse them, right? So this is one beautiful property, and we have shown antibiotic properties of silver nanoparticles because, as you know, silver shows very good antibiotic properties. Sophrolipids also show antibiotic properties, and what we have seen is that when you combine these two, sophrolipid capped silver nanoparticles, they even become more potent antibiotics, very highly potent antibiotics that they kill the bacteria at very, very low concentration. Okay, so that is one thing that we did. As I said, let us talk about now functional dresses. We made water dispersions of nanoparticles, and they showed one property like basically killing the bacteria. Now let us try to make functional dresses, right? Not just the organic molecule on the surface is not sitting there to protect, but is also giving some functionality to the nanoparticle surface. Like these dresses are giving some functionality to the persons that these dresses are being worn. A person wearing this dress, as I said, is going for a function like wedding. This person is going for a war. This person is going for mountaineering, etc., etc. Right? Similarly, we wanted to make functional dress nanoparticles. Right? So for that, we choose another molecule called galen gum. Galen gum is again an interesting molecule. It is a carbohydrate. It is also a sugar. It can be consumed. It can be eaten. You can have it. Right? It is actually added as food additives. It is approved to be consumed. Right? It is also natural. It comes from food sources. Okay. So you have this galen gum, and which has actually not only this carbohydrate which can act as a reducing agent, but it also has one molecule called glucuronic acid. Glucuronic acid, right? And this glucuronic acid at an appropriate pH becomes glucuronate. Glucuronate, COO minus, not COOH, right? So once you make the nanoparticles, what we have seen is this glucuronate is exposed to the surface. Means these nanoparticles are not only capped by a molecule, but they are also having a charged surface on the top, right? And so there is a normal dress, but there is also charge on the surface, right? So what we thought is these charges can be used for attaching some other molecules. And for this, we chose, because these charges are these are negatively charged particles, or the surface charges are negative, we wanted to put a positively charged molecule on the surface. And we chose a molecule called doxorubicin hydrofluoride because it has a positive charge here, right? So these positive and negative charges interact, and what we could prepare is a composite of gold nanoparticles, gallium cap with a doxorubicin. So what is this application for, or what is the application that we can use this for? So these nanoparticles can be used to deliver this drug called doxorubicin, and it can be used to deliver them into brain tumor cell lines, right? So it is very difficult to deliver drugs into brain tumors because of a particular phenomenon called blood-brain barrier. So we could show that, using this gallium cap particles, we can even deliver drugs into brain tumor cell lines. Of course, we really did not show the animal studies to really prove the point of blood-brain barrier crossing, but it proves the concept that using such nanoparticles, you can indeed deliver drugs into brain tumor cells, right? We left it at that point because studying the brain tumor cell in animals is not very easy, right? So, but this is a concept that we proved, that using gallium cap particles, you can decorate anti-cancer drugs, and then those nanoparticles can deliver this drug into the brain tumor cell lines, right? So that is the second example we showed. And then I want to spend last few slides of mine and showing multifunctional dresses. We showed water dispersions of nanoparticles. We also showed water dispersions plus charges that can be used to load drugs. But now you can do multiple tasks using these nanoparticles. Again, as an analogy, I want to show this particular example. These two people wanted to get married, and for whatever reasons they wanted to get married while skydiving, right? So it's so dangerous. Not only getting married is dangerous, but even skydiving is very dangerous, right? But they somehow wanted to do it, but to protect themselves or to give them that multifunctionality, what they did is, apart from wearing the wedding gown, etc., what they did is they also added a parachute, right? Not only these two people, even this person who is actually holding a Bible so that these two people can marry while diving, so he is also wearing a parachute, so they all can land safely, right? So this is the multifunctionality I am talking about. Not only they are able to get married while skydiving, but they are also able to protect themselves from safe landing, right? So these are the multifunctionality that these people have thought about. Also, in the same context, you can also disguise, right? So this is my favorite example. So here you can see two photos, and then obviously this person looks like a beggar and this person looks like a rich man. And if I want to really reveal the secrets here, so this person is none other than Sonu Nigam, Mr. Sonu Nigam, who is a famous Bollywood singer, and I am sure even in Telugu he must have sung some songs. So basically this guy is same. This is also Sonu Nigam. It's just that he put this dress and was sitting on a pavement in Bombay and then was singing like a beggar. Nobody cared. No one cared for Sonu Nigam when he was singing on a pavement, right? But when the same evening he said, I am Sonu Nigam, I want to sing, please pay 1,000 rupees. People were fighting for the tickets. Here he was begging for 1 rupee, nobody cared. Here he was demanding 1,000 rupees, everybody was fighting, right? So that is the difference you can do by putting an appropriate dress on the surface. You can disguise, you can cheat in a sense people, right? So here also we wanted to cheat cancer cells, and for that what we did is we wanted to make a protein cap nanoparticle, right? Previously I showed about a sugar coated nanoparticle. Here I am talking about a protein cap nanoparticle, and for this reason, for this purpose, we chose a protein called bovine serum albumin. And this bovine serum albumins are actually food for the cells, right? And what we thought is, let us coat the nanoparticles with bovine serum albumin and also coat the nanoparticles with a drug against cancer. So the reason is like this. What is cancer? In a simple term, cancer is nothing but uncontrolled division or growth of cells. Uncontrolled division or growth of cells. In a controlled division of cells, the old cells or the mother cells or whatever the previous cells die at some point, and the new cells keep on growing, the daughter cells keep on growing. But if this is not controlled, there is no death happening to the mother cells or the previous cells, then it becomes cancer, right? But any uncontrolled division or uncontrolled growth, right? Here you can think of a person who is, let us say, very fat, right? So any uncontrolled growth can happen due to many reasons. But one of the reasons is that eating food uncontrolled, right? And if you eat food uncontrolled, you know what are the consequences of that. Cancerous cells, because they want to grow uncontrolled, they also need lot of food. And this bovine serum albumin is a food basically for the cells. So what we thought is, if we feed normal cells and then the cancer cells this bovine serum albumin capped particles, these cancer cells will take more of food because they are growing very fast. When they are growing very fast, they will take more food, which means more bovine serum albumin. But along with the food, we are also adding an anti-cancer drug. So unknowingly, they are taking this drug along with their food, right? Basically, you are basically poisoning their food, right? So, but they are thinking it is food and they are taking it. So we thought whether this concept will work, and therefore we made this bovine serum albumin capped particles. Don't worry about again all the details. But what we did is, to prove our point, we loaded these bovine serum albumin particles with a drug. Here I am not showing the example of the drug, but we are showing the example with a dye, right? Dye and drug basically. So what we did is, we fed these nanoparticles to two different cell lines. One is what is called a fibroblast cell lines, normal cell lines. NIH3T3 is their trade name, or their available name. And the other ones are a tumor cell lines, cancerous tumor cell lines, or brain tumor cell lines, as I have in the previous example shown. And we fed these nanoparticles loaded with the dye molecules because we wanted to see whether the nanoparticles are preferentially taken, right? So we fed them at the same time, and after about 2 hours, we took the examples and we saw the cells under a microscope, right? What you can see here is that this BSA capped gold nanoparticles loaded with a dye called a Texas red, you don't see much of a dye inside, right? Except very small amount here, right? See, these cells also want the food. They also want to take the food. But these cells, because they want to grow faster, uncontrolled, they take more of food. Around the same time, these are taking more food, these are taking very less food, right? But along with this food, there is this dye or drug that is being delivered. So therefore, these cells get killed, right? Whereas these cells, because they are taking lower amount of food, they might survive for longer periods of time. So they get preferentially killed and they don't get killed. This is the idea, right? So we showed that, and then basically published a paper. We are pursuing this kind of work, etc. So to conclude now, let me give some time for some discussion, because 10 to 12 was the time that was given. To conclude, what I have shown is that we can make functional nanoparticles as organic dispersions, and these are good for electronic applications and they have great stability. But you can also make functional nanoparticles as aqueous dispersions, right? And which can be used for applications like drug delivery, etc. And they have good biocompatibility. Okay. So, and you can not only make one type of a dress, you can not only put one type of a dress, you can put multiple layers of dresses on the nanoparticles, and then they can basically do multiple jobs for you once they are taken inside the body, right? So this is the ultimate target that people are now looking at, researchers are looking at, right? To add multiple functionality to the nanoparticles. So with that, I hope I could convince you that like a tailor takes a kind of a raw piece of cloth or a rag kind of a thing and converts them to a beautiful dress that people wear. Similarly, we take a metal precursor, a raw material, a metal salt, and use our molecules here using some tools like machine, scissors, string, etc. We take organic molecules and convert them into this beautiful functional material, right? So this is what we do in the lab, and such nanoparticles, functional nanoparticles, have many applications. So what you need to understand is that each of these applications, you cannot use the same nanoparticle. You have to define the functionality. You have to define the function, and for that function, you need to make a nanoparticle. Many a times, when I think people doing research, I see they say that I have a nanoparticle. What is this application? Or what can their applications be? I think this is not a correct strategy. The correct strategy is to first take out an application or fix an application, and based on that application make your nanoparticle or make your nanomaterial, right? Not that you first make the nanoparticle and look for an application. That is not a correct strategy. You need to always go the opposite way. First fix an application. This is the application that I want, and for that what kind of a nanoparticle I should prepare, and how do I surface functionalize or put a dress on the surface so that that can be used for such application. I think this is an extremely important thing that people need to do. With that, thank you for your kind attention. I'm sorry for some technical glitches in between. I hope after that initial glitches there was no problem. I talked them through freely. I hope that. With that, thank you very much, and I will be happy to take any questions or comments.
Thank you very much, sir. From the bottom of my heart, for taking time from your busy schedule to be with us today and for the excellent presentation. Our seminar was a huge success. All thanks to your enlightening words that inspires many young minds, sir. You are a good teacher too. Now it is time for interaction. I call upon our delegates and students. If you have any queries, you are free to ask. Dear students, if you have any doubts, unmute yourself and ask for the doubts.
Yeah, please, whatever questions, don't worry about, it can be anything, not even from the talk. You can ask me anything. To the best of my ability, I will be able to tell you. And I will prefer if the students take the initiative and ask me questions.
Any queries, dear students? If not, we'll proceed to the last part of the program. For me, every hour is grace. I would maintain that thanks are the highest form of thought, and that gratitude is happiness doubled by wonder. Joy is the simplest form of gratitude. Sir, once again, thank you for bringing out the importance of clarity of thought, curiosity, and courage, which is the need of the hour for the students. And as we have come to the end of the program, I invite Dr. K. Swarnalatha, Associate Professor in Chemistry, to propose vote of thanks. Over to Swarnalatha, ma'am.
Good afternoon to one and all. Let us grateful to people who make us happy. They are charming gardeners who make our souls blossom. Teamwork makes the dream work. This afternoon, all our hearts join together with appreciation and good wishes. On behalf of Department of Chemistry, Ch.S.D.St.Theresa's College, Eluru, it's my honor and privilege to express few words of gratitude to this distinguished, intellectually stimulating gathering. Our first and foremost thanksgiving goes to God Almighty, the creator of you and me, for what we have and for what we don't have. May his name glorified above all other names. Thank you, Lord, for blessing us so bountiful. Appreciation is the highest form of prayer. for it acknowledges the presence of good wherever you shine the light of your thankful thoughts. My sincere thanks and appreciation goes to our management sisters, Dr. Sister Marita Pudota, Superior and Correspondent of our college, our dynamic principal, Dr. Reverend Sister Marita Dimello, and Vice Principal, Dr. Reverend Sister Shaurilu, and Office Superintendent, Reverend Sister Inyasamagaru, for their constant support, encouragement in all the enormous cooperation in organizing this national seminar. Our sincere and special appreciation, thanks, and blessings goes to today's resource person, Bhagavathula L.V. Prasad Garu, Director CENS Bangalore, Senior Principal Scientist CSIR NCL Pune, for sharing highly valuable, rich, acknowledgeable aspects related to many aspects: career planning, success stories of different great persons, interesting properties and applications of nanoparticles, and advantages of the dressing nanoparticles, and so many interesting aspects of the nanoparticles and their applications in treating the cancer. My sincere thanks to all the HODs of the various departments for their continuous support. My sincere thanks to all the teaching fraternity, supporting staff, technical staff for their cooperation. I take this opportunity to thank dear students for adding joyful spirit to this national seminar. My heartfelt congratulations to the organizing team for your hard work, which made this seminar a great success. I thank all the participants. Your presence in the seminar spoke volumes. Thank you, one and all.
Thank you, Miss, for doing the noble task of proposing vote of thanks. Once again, I deem it a privilege, and we are indeed fortunate to have DLV Prasad Garu with us. Sir, we would like to have many more interactive sessions with you, and we need a lot of advices and suggestions as we want to go through research in the form of nanotechnology. So looking forward to have many more interactive sessions with you, sir. And heartfelt thanks once again for the excellent presentation. Thank you very much, sir. And I thank everyone, all the delegates, students, and all the participants for your for sparing your precious time and coming for the national seminar. Thank you, one and all.
Thank you, and I take up. Thank you very much.